Exercise 6.5. The equation of the plane pi1 is given by r is equal to 2i minus 11j plus 5k plus lambda times 4i plus 2j plus 7k plus mu times 5i plus j plus 8k. Find a Cartesian equation of the plane. Now, I'll note that it says find a Cartesian equation of the plane. They're all the same. It's just that I guess you could multiply both sides by a constant. So if you have ax plus by plus cz equals d, and it's the same plane as ex plus fy plus gz equals h, then this implies that a is equal to ke and b is equal to kf, etc. So, they are unique up to multiplying both sides. Well, d is equal to k times h. They are unique up to multiplying both sides by some constant k. Anyway, back to the problem. So I'm going to write it in a slightly different form, just because that's the one I prefer. So r of lambda mu is equal to 2 negative 11 5 plus lambda times 427 plus mu times 518. And we see that this 2 negative 11 5 is a vector that takes us from the origin onto the plane. So this can be our plane pi1. So this, let's say this point here is P. Then the vector OP is this one here. And then we have two direction vectors, 427 and 518, that the plane is parallel to. So this vector is inside the plane. Let's say it's the vector PQ. And then there's also another direction vector from the point P to another point inside the plane. Let's call it R. So this one here can be PR. Now, in order to find our Cartesian equation of this plane, we need a normal vector n. And the way to do that is to take the cross product of PQ and PR. So n is equal to PQ cross PR. So that would be 427. Oh, I gotta be a bit careful. Actually, if I do PQ cross PR, my normal vector would point down in that direction because of the right hand rule. It doesn't really matter because this is just a diagram, but just to make it so that it's more clear, I'm gonna redo this. So n is equal to actually PR cross PQ, according to my diagram. Again, it doesn't really matter, but it just makes it a bit clearer here. Don't want to confuse people. Okay, so PR is 518, and then it's crossed with 427. Okay, so the first one is 7 minus 16, so that will be negative 9. For the second one, we delete the second row, and then we do the determinant, but backwards. We take the negative of it. So it's going to be 4 times 8, which is 32, minus 5 times 7, which is 35. So that's going to be negative 3. And then lastly, we delete the last row. It's going to be 5 times 2 is 10, minus 4 times 1. So 6. And then finally, note that if x, y, z is any arbitrary point in the plane, then the vector that goes from P to the point x, y, z, dotted with the vector n, is equal to 0. Another way to write that is x, y, z minus OP, which is 2 negative 11 5, So this is, let's call it the vector v that goes from P to xyz, where xyz is an arbitrary point in the plane. So this is the vector v here, and we know that v dotted with our vector n is equal to 0. And using the linearity property of the dot product, we can split this up into x, y, z dotted with n, which is -9, -3, 6, is equal to 2, -11, 5 dotted with n. So -9, -3, and 6. By the way, if you don't want to use -9, -3, 6, you can actually use any multiple of it. Remember, it doesn't matter which vector we take, which vector n we take, as long as it's normal to the plane. So if, in fact, any vector k times n will do. So if you want to divide them all by 3, which looks like a good thing to do here, that's fine too. So x, y, z dotted with -3, -1, and 2 is equal to 2, -11, 5 dotted with -3, -1, and 2. And from there we get -3x minus y plus 2z is equal to 2 times -3 is -6 plus -11 times -1. So -6 plus 11 makes 5, plus 5 times 2 is 10, so 5 plus 10 makes 15. So that is one Cartesian equation of our plane. And of course we can also times it by -1 if you really want the coefficient of the x to be positive. So 3x plus y minus 2z is equal to -15. That's also fun.